Welcome, everyone. My name is Pablo García-Linares, and I work at the Solar Energy Institute at Technical University of Madrid, UPM. I'm going to present our work on hybrid thermionic photovoltaic cells, which we have designed and fabricated and characterized using a back contact 3-terminal configuration. This is the outline of the talk, where some definitions on thermophotovoltaic, TPV, and thermionic TI converters will be addressed in order to introduce the novel thermionic photovoltaic TIPV concept we are trying to develop and characterize. I'll then show the preliminary results which allow the proof of concept employing a two-terminal architecture in order to introduce the advantages obtained using a three-terminal approach. I will then explain the TPV cells implemented for this purpose and the optimum design obtained, which lacks metallic fingers in its back contact configuration. Finally, the characterization of such devices will be shown. To provide some context, we will briefly define both TPV and TI independently. As everybody in the audience probably knows, a TPV cell is capable of absorbing the low-energy photons, infrared radiation, emitted by an incandescent source, what we call emitter, by a low-energy bandgap semiconductor PN junction. A photocurrent is produced as well as an output voltage, which implies that an electrical work is produced out of the infrared radiation. On the other hand, TI devices collect the electrons emitted by a low work function cathode, also producing an electrical current and voltage. If we now merge both TI and TPV concepts, we obtain the novel TIPV device. These hybrid converters can make an efficient use of both electrons and photons emitted out of the TI cathode surface. In this case, the electrons are collected by the TI anode, which is transparent to the infrared light that is directed towards the TPV PN junction. As a result, an electrical work is also produced. As advantages of this new paradigm compared to a conventional TI converter, losses can be reduced because now photons can also be converted into electricity and not only electrons. Then, compared to both TI and TPV, a higher power density can be achieved because both photons and electrons emitted from the source can be converted. We have to recall that in such kind of devices, not only the efficiency, but also the power density obtained is particularly important. Finally, compared to TPV and near-field TPV, where very high electric current densities can be produced, the TIPV lacks lateral majority carrier transport because such conduction is made through a wireless 1D direction, because the rear side of the cell can be fully covered by metal, thus producing negligible ohmic losses. Regarding this, a poster by Dr. Alejandro Datas will be shown on Wednesday. The TIPV proof of concept was already successfully carried out with a two-terminal device using a conventional gallium arsenide photovoltaic cell and introducing it into a vacuum chamber at Zehender in Italy, where a tungsten incandescent source is approached while monitoring the current and voltage characteristics. When comparing the results from a purely TI converter, that is, an anode made of only a p-type gallium arsenide, we obtain the red curve. However, if instead of a p-type gallium arsenide anode, we put a gallium arsenide PN junction, thus forming the two-terminal TIPV cell, that is with the TI converter connected in series with the TPV1, a significantly higher voltage can be extracted from the device. The proof of concept could also be improved by depositing a cesium layer that further lowered the work function of the anode, which showed an enhancement of nearly 1 volt in the voltage observed. A work related to this type of measurements will take place on Wednesday on the advanced concept session. We now need to point out the two strategies defining different device configurations that a TIPV cell can adopt. On the one hand, the two-terminal approach that we had showed previously in the last slide. It hosts the TI converter series connected to the TPV cell so that it injects electrons in the valence band of the P side of the TPV junction, which can now be pumped to the conduction band, creating a photocurrent that closes the circuit. This series connection imposes a unique current flowing through the device. Alternatively, the three-terminal approach can face the N-type substrate of the TPV cell to the TI cathode, since both cells work independently and are electrically decoupled. In this case, they share a common contact, TI anode and a TPV junction N side, from where the two independent electrical circuits can be accessed and biased. The devices we show in this work are aimed at implementing this approach, where a back contact configuration is required. Regarding the advantages of this three-terminal TIPV architecture, in this case, an N-type TI anode can be used so that a lower work function compared to a P-type one can be obtained, allowing the production of a higher voltage. As we have also mentioned, this way the TI and TPV subcells are electrically decoupled, and therefore there is no need for current matching, which allows independent biasing of each subcell, resulting in lower losses and a higher power generation. Finally, as we can observe in the graph from the seminal work that introduced this TIPV concept, when using a three-terminal architecture, a higher power can be delivered throughout a wider temperature range, meaning that the TIPV converter is more flexible than the two-terminal one when the operation conditions vary. Let's now move forward to explain the work on TPV cell fabrication. We began with the epitaxy of InGaAs cell structures on top of an indium phosphide substrate, with which we first fabricated small concentrator upright devices, which we processed, diced, and encapsulated. We then performed photovoltaic device characterization, such as this family of IV curves under concentrated light, which show a pretty good fill factor at current densities as high as 75 amperes per square centimeter. This showed that we could move forward from the small and conventional front grid upright configuration to the back contact interdigitated one. And so we did, designing and implementing the first approach to a large area interdigitated indium gallium arsenide devices, where both contacts could be extracted from the rear side and the illumination could come from the front side through the substrate. Here we can observe a magnification of the interdigitated gold grid, which final appearance is this other one with two big pads where a handmade contact could be done. It has to be pointed out that the size here is 1 square centimeter. So in this case, the current densities of the previous concentrator cells would never be achieved. These cells were characterized either with front and rear illumination, resulting in a very promising performance when illuminating through the substrate, as we had planned them to be used for. This way, we can verify that the indium phosphide filters out all the light above approximately 920 nanometers, the indium phosphide bandgap, before it reaches the indium gallium arsenide junction. This is not supposed to be a problem for our TIPV characterization purposes, since the spectrum of the hot emitter between 13 and 1400 Celsius degrees does not produce an important response on these cells. Once the first interdigitated cells had been tested, we wanted to redesign them so the finger pitch was optimized and produced the minimum lateral conduction losses. For that purpose, we used a quasi-3D distributed model fed with semi-empirical electronic parameters such as material carrier mobilities, reverse saturation current densities, sheet metal and specific contact resistance, etc. Once the different unit cells corresponding to illuminated area with or without PN junction were defined with a particular grid design, the whole circuit with thousands of nodes was solved by SPICE software. The simulation produced a surprising result where the optimum was reached for a finger pitch as large as possible and a finger width as small as possible. These two conditions result in a fingerless configuration that is a rear contact fully covered with metal and front contact as small as possible. This was enabled by the fact that the photo-generated electrons flow through the N-type indium phosphide substrate, which behaves equivalently to a gold metal sheet in terms of lateral conduction, sheet resistance, until reaching the small top contact. In the case of the holes, they flow vertically until they directly reach the metal contact. In the end, instead of a real interdigitated design, what we obtain is a fingerless architecture, which is why we have called it this way. These large area fingerless devices are processed, they are encapsulated on an isolated metal substrate, IMS, which helps with the thermal management necessary, taking into account the high temperatures involved in the process. The fingerless cells are then flipped, exposed the indium phosphide substrate, and encapsulated using a low temperature soldering paste. Now they are ready for the characterization. Here we show their quantum efficiency, which is promisingly good, taking into account that no anti-reflection coating is being applied yet. Concentrated light IV curves show a relatively good behavior up to 1 ampere per square centimeter, which is usually high enough for the intensities generated when characterized as TIPV cells. These cells have also been characterized with the TPV efficiency measurement setup we have recently developed. A talk on this system will take place on Thursday, but we can advance that it is based on a vacuum chamber where an emitter is heated by a laser and a pedestal maintaining the cell at room temperature while measuring the heat flux through it. Our cell has only been measured up to 900 degrees, showing an efficiency of 1.6%, probably due to the low temperature, the lack of back reflector, and the thick indium phosphide substrate that filters out the energetic photons and produces a very large free carrier absorption of the infrared light. As a conclusion, TIPV experiments had only been demonstrated on gallium arsenide 2-terminal devices, while 3-terminal ones offer significant advantages. Therefore, we have modeled and optimized interdigitated back contact in indium gallium arsenide cells, resulting in a fingerless design where current flows through the substrate. So now fingerless devices are ready for TIPV 3-terminal experiments, which are the next steps that will be carried out by our Italian colleagues at Zehender, this time using an indium gallium arsenide junction. Thank you very much. I'm now happy to answer your questions.